Have you ever wondered what makes quantum computers so groundbreaking? These machines operate on principles that defy everyday logic, promising a whole new era of possibilities. Welcome to Whiteboard Doodles, the channel where we simplify tech-related concepts using whiteboard animations. Today, we'll uncover the mysteries of quantum computing, what it is, how it works, and the incredible ways it could reshape our world. Let's dive in. First, let's take a brief look at what quantum computers are. Quantum computers are advanced machines that harness the principles of quantum mechanics to process information in a fundamentally different way than classical computers. Instead of using bits, which represent data as zeros or ones, quantum computers use qubits, quantum bits that can exist in a state of 0, 1, or both simultaneously, thanks to a property called superposition. This enables quantum computers to perform multiple calculations at once. Additionally, qubits can be interconnected through entanglement, allowing them to share information instantly, regardless of distance. Together, these properties enable quantum computers to solve certain complex problems much faster than classical computers, making them ideal for tasks like cryptography, optimization, and simulating molecular structures. However, they are still in the early stages of development and face challenges like error correction and maintaining stable quantum states. To understand how quantum computers work, it's important to know their key components. At the heart of a quantum computer are qubits, which, unlike classical bits, can represent 0 and 1 at the same time using quantum mechanics. These qubits are controlled by a quantum processor, which uses special quantum gates to perform calculations. To keep qubits stable, the system needs supercold cooling systems that bring the temperature close to absolute 0, reducing any interference from heat. Error correction systems are also essential to fix problems caused by the fragile nature of qubits. Finally, control electronics connect the quantum computer to classical computers, sending instructions and processing results. Together, these parts allow quantum computers to tackle problems that traditional computers can't handle. Now let's take a closer look at how a quantum computer actually works. When a quantum computer receives a task from a regular computer, the process begins with the instruction being translated into quantum operations. For example, imagine we need to solve a maze to find the shortest path. The regular computer breaks down the problem into a form the quantum computer can process and sends it over. Inside the quantum processor, the qubits represent different possible paths in the maze. Using superposition, each qubit holds multiple possibilities simultaneously, effectively exploring all paths at once. Quantum gates then apply operations to adjust the probabilities of each path, guided by the rules of quantum mechanics. These gates amplify the likelihood of the shortest path being the correct solution while suppressing incorrect ones. This process is controlled by precise signals from the control electronics. Throughout the computation, error correction systems monitor and ensure the fragile qubits stay in the right state. Finally, when the calculation is complete, the quantum states of the qubits collapse into classical bits, revealing the shortest path. The result is sent back to the regular computer, which interprets it as the solution. This seamless interaction between classical and quantum systems is what makes quantum computers so powerful for certain types of problems. As quantum computers continue to develop, their potential applications are becoming increasingly clear. These machines can revolutionize cryptography by breaking traditional encryption methods while enabling the creation of quantum secure systems. In medicine, quantum simulations could lead to the discovery of new medications and materials by modeling complex molecules and their interactions. Artificial intelligence and machine learning can benefit from quantum speedups, enabling faster training of models and improved optimization. Quantum computers can also enhance logistics and supply chain management by solving large-scale optimization problems, like finding the most efficient delivery routes. Even in climate modeling, their ability to simulate and analyze vast amounts of data can help researchers predict environmental changes more accurately. To learn more, check out our videos on cryptography, AI, and machine learning in the description for deeper insights into how these fields connect with quantum computing. Despite its immense potential, quantum computing faces several significant challenges that must be overcome before it can achieve widespread practical use. One major hurdle is the fragility of qubits, which are highly sensitive to their environment and prone to errors caused by even the slightest disturbances, a problem known as decoherence. Maintaining the precise conditions required for quantum operations, such as ultra-low temperatures and specialized cooling systems, adds to the complexity and cost. Additionally, developing effective error correction methods to manage the instability of qubits is a critical area of research. The lack of a robust quantum programming ecosystem also limits accessibility, as current quantum algorithms require highly specialized knowledge. Furthermore, scaling quantum computers to include more qubits without increasing error rates remains a daunting technical challenge. While these obstacles are substantial, ongoing advancements in materials science, algorithm development, and engineering bring us closer to unlocking the true power of quantum computing. As quantum computing advances, it raises important ethical and security concerns that must be addressed. One major worry is its potential to break current cryptographic systems, rendering many forms of online communication, banking, and data storage vulnerable to breaches. This could expose sensitive information and disrupt global security infrastructures. Additionally, the uneven access to quantum technology might widen the gap between technologically advanced nations and those without the resources to develop or utilize these systems, creating disparities in innovation and security. Ethical questions also arise regarding the use of quantum simulations, particularly in fields like artificial intelligence, where the technology could accelerate developments that outpace regulatory frameworks. Ensuring the responsible development and use of quantum computers will require global collaboration, robust ethical guidelines, and proactive measures to create quantum-resistant security systems. In conclusion, quantum computing represents a revolutionary leap in technology, offering unprecedented capabilities that could reshape industries and solve problems once thought insurmountable. From enhancing cryptography and advancing medicine to optimizing logistics and accelerating AI, its potential is vast. However, realizing this future depends on overcoming significant challenges, such as qubit stability, scalability, and ethical concerns. While still in its early stages, ongoing research and innovation are paving the way for quantum computers to transition from experimental tools to practical, impactful solutions. As we stand on the brink of this new era, it's crucial to approach quantum computing with both excitement and responsibility, ensuring that its benefits are harnessed for the greater good. This marks the end of our exploration of quantum computers. If you enjoyed it, consider subscribing to our channel and liking the video. Feel free to also check out our other videos on related topics. Thank you for watching.